I'm going to talk about subatomic particles. We talked about how the atom is the smallest building block of matter, but also how we have come to realize that there are smaller pieces within the atom. And every atom contains the same subatomic particles. There are others that we're not going to talk about, but the major ones are protons, neutrons, and electrons, and those are the ones we're going to be concerned about in chemistry. Protons and neutrons have nearly identical masses. If you measure the mass in kilograms, they differ in the fourth significant digit here, 1.672, 1.674, times 10 to the minus 27 kilograms. These guys are very, very small. The electron is even smaller, 9 times 10 to the minus 31 grams. It's a little hard to compare numbers like that that are so small. So if you think about a baseball and a grain of rice, if a proton had the mass of a baseball, then an electron would have the mass of a grain of rice. So the electrons are very, very small compared to the protons and the neutrons. The unit kilogram or even the unit gram, even like nanogram or picogram, is still way too large to be convenient for measuring the mass of atoms. And so we created a new unit to measure the mass of atoms. And it sounds a little, I don't know, flip. Oh, we just made up a unit. Where did all units come from? Someone made them up, right? It's not an intrinsic part of nature that there are units. The foot was originally the length of the king's foot, right? And there were different things like that. So making up a unit is not a strange thing. This unit is called the atomic mass unit. Not a very catchy name, but it is descriptive. It's for measuring the mass of an atom. And the abbreviation is AMU, not AMU or AMU, some strange relative of an emu. It's just AMU. 1 AMU is 1/12 the mass of a carbon atom containing 6 protons and 6 neutrons. And that may seem like a strange way to define a unit. And if you don't really grasp that, it's okay. But we'll see in a few minutes why the definition of this is significant. That makes the mass of a proton or a neutron approximately 1 AMU. We know that the charge on an atom is 0 overall. If it has electrons and protons inside, they do have electrons and protons inside. The electrons are negative, the protons are positive. Their charges are equal in magnitude but opposite in sign. So the proton, we say, is a +1, the neutron is 0, and the electron is -1. So the relative charge here is something that you need to know. The actual charge measured in coulombs, we're not going to use that number very much, and if we need it, we'll just look it up. It's 1.6 times 10 to the minus 19 coulombs. The electron is exactly opposite, negative in charge. Here are the masses in kilograms. We've seen those. These masses are more useful. A proton is approximately 1 atomic mass unit. A neutron is approximately 1. The electron is about 1,800 times smaller, and so sometimes it's just not significant at all, and so we kind of ignore the mass of electrons at times. What identifies an atom as being a particular element is the number of protons in its nucleus. Neutrons can vary a little bit, electrons can be gained or lost, but the number of protons says you are an element, you belong to this element. Number of protons is called the atomic number. They gave it the symbol Z. Don't ask me why, it doesn't make any sense to me either. But the atomic number is the number of protons, it has the symbol Z. Here we have an illustration of a helium atom. In its nucleus are 2 protons. All helium atoms have 2 protons. Here is a carbon atom. There's carbon in the graphite of your pencil, every carbon atom has 6 protons in its nucleus. If it has a different number of protons, it's a different element. On the periodic table, there is a lot of information, and we'll be learning about it as we go along. Here what we want to point out is we have the chemical symbol, that's 1 or 2 letters, and then above it is a whole number, and that is the atomic number. So on the periodic table, which you will always have access to on an exam, we'll have the one on the wall, and I'll also give you a clean blank periodic table that you can use and do whatever you want with. So we'll always have this. So we can look at this and say, oh, beryllium. Every beryllium atom has 4 protons in its nucleus. We could look at gold. Every gold atom has 79 protons in its nucleus. So that information is right there on the periodic table. Each element has a unique atomic number, and it also has a unique chemical symbol. And I've already made you memorize a whole bunch of those, right? Those chemical symbols are 1 or 2 letters. The first letter is always capitalized. The second letter is never capitalized. And when you write, I know that some people like to do all caps, but if you're writing, say, the symbol for neon, that's a lowercase e. You can't just make a small capital E. This is not acceptable in my class. It has to be a lowercase e. All the rest of your handwriting, if you want to write small caps, I'm fine with that, but not in your chemical symbols. A lot of the chemical symbols correspond to the element's name, but some of them correspond to the Latin or Greek names by which they were originally known. That's why sodium, that starts with S, has the symbol Na, because it was originally called natrium, and that's the first 2 letters of the Latin name for sodium. So all atoms of a given element have the same number of protons, but they don't necessarily have the same number of neutrons. And this is one of the components of Dalton's atomic theory that we had to revise because we found out that that wasn't quite true. So looking at neon, all neon atoms have 10 protons, but they could have 10, 11, or 12 neutrons. So there are 3 different versions of neon atoms. Each one is going to have a slightly different mass because the protons and the neutrons are the particles in the atom that have mass, significant mass. And so if you add an extra neutron in there, that's going to change the mass of the atom a little bit. And so the masses will not be exactly the same. So we use this word isotopes to describe atoms that have the same number of protons. They're the same element, but they have different numbers of neutrons. Isotopes. Iso is a prefix that means the same. They're the same element, but they're a little bit different.
It's usually more than less neutrons than protons?
The relationship between number of protons and number of neutrons is, it kind of varies. There are some patterns in it, but they're not real obvious.
But they're usually more neutrons.
Usually there's more neutrons than protons, but occasionally there are less. Like the hydrogen atom, the one known as protium only has 1 proton and no neutrons. And so there it has fewer neutrons than protons. Yes?
Is this where you get the different, I don't know what you call them, it's like when you write them down, you'll have like, what did we use? Iron, for example, Fe3 or 2. Is that what we could
No, I think you're thinking of the charges.
Okay.
And so that's going to be a little bit different. So many elements have more than one isotope, but some of them only have a single isotope. There's only one kind. And this information we do not find on the periodic table. There's just not really any clue, and there's not really a set pattern of which elements have isotopes and how many they have. This is something that's discovered by experiment. They look at the different atoms and they find out the different masses. And then what the relative number of each of them is. If you have 2 isotopes of a given element, that does not mean that half of them are one isotope and half are the other. So we call it a natural abundance. You look in nature and you measure different samples of that element, and you find that the relative natural abundance is fairly constant. It's not exactly the same all over the Earth, but it's relatively constant. So these are called natural abundances. We usually give this in terms of a percentage. We'll say, okay, well, 75% is this isotope and 25% is the other isotope. There can be more than two. There can be 3 or 4. Mass spectrometry is what has allowed us to measure more accurately the different masses. And so we find that there are small but significant variations in that natural abundance. We're not going to have to worry about that, but you know, I try not to lie to you. I have to lie to you sometimes for your own good, but I try not to. So the number of neutrons plus protons is called the mass number. And that kind of makes sense. Neutrons and protons are the particles that have mass, and so you add those together, and that's the mass number. The mass number is given the symbol A. I do not know why it's A, but it is. So A equals the number of protons plus the number of neutrons. And we have a couple of different ways to indicate which isotope we're talking about. This is what's often called a nuclear symbol. Here we use the chemical symbol, the 1 or 2 letter abbreviation for the element, with a superscript and a subscript to the left of the symbol. The superscript is the mass number, that's protons plus neutrons. The atomic number is just the number of protons, and that will be a subscript on the left. So for neon, these are the symbols for the 3 different isotopes. One of the nice things about this is if you need to know, well, how many neutrons does this isotope have? All you have to do is take those numbers and subtract. That one has 10 neutrons. This one has 11, and this one has 12 neutrons. So the symbol doesn't directly tell us how many neutrons, but we can figure it out with a very simple subtraction. Another common notation is to use either the chemical symbol or the name, followed by a dash and just the mass number. This doesn't give us the atomic number, but we have periodic tables, and so we could look that up very easily. So neon 20, Ne20, this is the isotope that has a mass number of 20. And we've got neon 21 and neon 22. Any questions? Yes?
So why are there decimal places? Is that like for the electron?
Why are there decimal places? You mean in the red numbers under the symbols? Yeah, we'll get to that. We'll get to that. We're coming up to that really quick. Yes?
What was the AXZ thing? What was the name of that again?
Well,
The name of that denotation?
this notation is often called a nuclear symbol.
Okay.
I'm not sure if there really is a name for this. It's an isotope name.
I see.
Sometimes we're concerned about which isotope we're dealing with, and other times it doesn't matter. Most of the time it doesn't matter, in fact, but we just need to know what this is for when that comes up. Any other questions? So here's a table from your textbook showing those 3 different isotopes of neon. Here are 2 different versions of the symbols for them. You'll notice that each of them has 10 protons because they're all neon, and all neon atoms have 10 protons. And then this gives the number of neutrons. Here's the mass number, which you see is protons plus neutrons. And then this is the natural abundance. This is determined experimentally. So 90.48% of neon is neon 20. Only 0.27% is neon 21, and 9.25% is neon 22. And you might ask, well, why is there so much more neon 20? I really can't answer that, because there is. And it's easier to answer why is the sky blue than to answer that one. So let's see, what do we need to be able to do with this information? We should be able to answer questions like this. What are the atomic number, the mass number, and symbol for the carbon isotope with 7 neutrons? Well, let's start with atomic number. The atomic number is going to be 6 because carbon is number 6 on the periodic table. That means it has 6 protons. So the atomic number is Z. I think it should be A, but they did it backwards. The atomic number is 6. That's the number of protons. What's the mass number? 13. It's going to be the 6 plus the 7 protons. So the atomic number, the mass number is 13. And then what would the symbol be? We've got the C, and we'd have 13 up here, and the 6 down here. That's 1. Or we can call it C13. Or carbon 13. And so there are 3 different symbols for that particular isotope. Any questions? Let's look at letter B. How many protons and neutrons are present in an atom of this guy? I would read that as potassium 39. 19 protons. This number at the bottom is the number of protons. So 19 protons, and then the neutrons is 20. We just subtract this and we get 20. So 20 neutrons. And that's potassium 39. Any questions? So the number of protons is constant. The number of neutrons can vary a little bit, but atoms don't gain or lose neutrons. It's either carbon 12 or carbon 13 or carbon 14. They don't switch around between themselves. The thing that can change is the electrons. The protons and neutrons are in the nucleus. They're at the core. They're like your soul, right? No matter what you do to your appearance, or you be in some horrible car accident, but you are still you, regardless of what your body looks like. You can dress up like Big Bird, but you are still you, right? The electrons are more like the clothing or the outer appearance of an atom. The electrons can change. Atoms can gain or lose electrons. And when they do that, the charge on the atom changes. A neutral atom has a number of electrons equal to the number of protons. Equal number of positive and negative charges, it adds up to 0. If you gain or lose electrons now, you have a charge. And so in chemical changes, atoms can gain or lose electrons, and they become ions. An ion is just an atom that has a charge. Positively charged ions are called cations, not cations, they're cations. I have positive feelings for cats. I like cats, and so cations being positive works for me. If you hate cats, you'll have to come up with something else. Negative ions, such as F-, are called anions. Anion has an extra N in it compared to cation. Anions are negative. You need to keep them straight because we refer to cations and anions a lot.